Okay, recording has started. So yeah, today we're going to continue on hypothesis testing. And again, this is the data file. Make sure you have it and opened. You should be able to. We can check the data file at during the first exercise. There's other things that you would like to do during the break. Not right now, but during the break, is to download something called G-Star Power. You just have to Google G-Star Power and download it for your version. It is a tool to compute statistical power analysis for very different tests. It can be used to compute effect sizes to display graphically the results of power analysis. And this is a free tool and is one of the mostly widely used tool in statistics. This definitely is definitely one of the most widely used tool for the for analysis, for power analysis. So you don't have to do it right now. Just have to Google and download it during the break. And couldn't see the file, the lecture 5 slides. Let me just pause the recording. So yeah, make sure you download G-Power, okay? G-Star Power. There are 2 readings included in the Dropbox and in the team, Microsoft Teams. Is that this one paper on it's an open science publication called F1000 Research. So that one is that gives a guide to the null hypothesis significance testing paradigm. From now on, I just call it NHST. Also talk about a lot of the commonly misunderstood concepts, such as p-values and all that. And I just found the other paper is a quick comment on misunderstandings about p-value. It's just like a quick report about how American Statistical Association clarifies the concept of p-value. Just found these as I was doing readings yesterday, and they're very helpful and they're quite easy to understand. A lot of the things that we're going to talk about the p-value today come from these 2 papers. So yeah, make sure you have some time to read these go over these papers. Very, very helpful. I'm going to do a quick recap. Last time we talked about point estimation and interval estimation. Most importantly, we look at the concept of confidence intervals, that there is a confidence multiplier suggesting that the thing that the population parameter that we're trying to estimate fall within a certain range or interval. So here is the equation again. So in this case, we're estimating population mean using sample mean x bar and standard deviation. Usually we don't know the standard deviation of the population, so we use sample standard deviation in place of the sigma there. And again, it's divided by a square root of n because we're using standard error as the standard deviation, right? Okay. We talked about how sample proportion, how that works for sample proportion. Sample proportion is a special case of sample means using data. So the proportion means that it's a percentage from 0 to 1. So in this case, the standard error bit is estimated using sample proportion and sample size. Right? And we also learned that when the sample proportion is 50%, the standard deviation for sample proportion is the largest. And we also can see that when sample size gets bigger, the interval becomes smaller, which means that our estimation becomes more and more accurate. We're going to use the data that I just shared with you to do a quick 95% confidence interval estimation. So this is an item from another different survey that they did during the pandemic, asking what opinions and lifestyle. So I've only included a one table from that this data set, the survey. So I'll share it with you on the screen. Okay. So this is the table, right? So here are some information about exactly what this survey does. The coverage, meaning of some of the terms, and all that, right? So this looked at how people's lifestyle changes during the COVID-19 pandemic lockdown. Table 4 is about working at home. If you're interested, I will share the whole data, the entire data from the statistics. I think this is the National Statistics Office. But the table 4 is about working at home. And you can see that a sample of 1,000 respondents, or actually a sample of 660 respondents, also provide responses to the question, first of all, have you worked from home? Right? And we want to estimate, in this exercise, we want to do an interval estimation for this answer, yes. And you can see that actually the survey already provided the lower and upper bound of the confidence interval, which means that they already been calculated, but we want to calculate it ourselves, right? So if you scroll down, I've already provided this little exercise here for the proportion of yes to have you work from home question. We only needed two statistics to get this done. The first is the p hat, because I don't have the hat symbol here, but p hat is the probability of answering this yes to the question within the sample. So that is 41.1%, right? So we can just we have to convert that into a percentage. So we just equals, let's use the data from here, B9 divided by 100, and we have 0.411. And the other thing we need is N, which is our sample size. You notice that for our case, the sample size is 660. Right? So we'll just enter 660. So now we have everything we need. We just have to fill in the rest. We need 1 minus p. Since we're doing everything by equation, we just use 1 minus C35. So now 1 minus p is 0.589. And then we need p times 1 minus p. That would be C35 times D35. So the neat thing about this Excel equation is that when you click within the cell that contains the equation, it uses color to indicate the components that are used, the cells that are used, the data that are used to calculate this value. So in this case, you see C35, and C35 has been highlighted in blue here, and D35 is highlighted in red. right? So P times 1 minus P, it just shows you, confirms that your equation is right. That's what I'm seeing, showing, okay? So to calculate the standard deviation for our sample proportion, we have to first divide this P times 1 minus P by N, which we further write. Select this, and we write equals. If you, for example, for your interest, if you start a formula, you always have to start it with equal sign, right? Write an equation, you start with equal, and then you can select data. In this case, this is P times 1 minus P, divided by N is our data here. You can see that once you clicked to select the data, it uses color to indicate which data cells is it referring to. So that's for the P times 1 minus P divided by N. And for the standard deviation, we need to square root this value. So for this, we can use the square root function sqrt using parentheses, and then use the mouse to select the middle of the parentheses, and then you select the value, and then you get that. Okay, so that's the equation that you'll be writing, sqrt parentheses G35. G35 is a reference to the G35 cell. So for those who are not familiar with Excel, this is how it works. So this is an equation called square root. And you can see under the equation, it shows you what argument does it take. In this case, it takes an argument of a number, which is the value is G35. So you got a standard deviation of 0.019. And then we can move on to lower bound and upper bound of this confidence interval. So the lower bound equals the estimate, which point estimate. So what is our point estimate here? Well, point estimate is P, so 0.411. So remember our equation, right? So let me bring on the equation again to see how it works. So the equation is really, you have a point estimator, which in this case is our sample proportion. Confidence multiplier, if we want a 95% confidence interval, we use 1.96. And the standard deviation of the point estimator, in this case, it's the square root of P times 1 minus P divided by N, which you already calculated. Okay. So that's that. So in this case, with lower bound, we have the point estimator here. Lower bound will be a minus, okay? So 1.96, right? So that we have to enter manually times, right? The standard deviation, which is the value to the left, H35. Okay? So that's our lower bound. So for the upper bound, we can just copy this formula. It's not that easy, but okay, if we copy the formula, let's see what happened, right? So if you copy the formula, if we just drag the formula, for example, okay, it doesn't give us the right value because now it refers to I35, right? So we have to change it back to H35. So now it refers to the right H35 plus, and I believe that D35 is also wrong. If you look at the one before, we have C35. So we change that back to C35. Okay. So H35 is the standard deviation. C35 is our point estimator. Let's go check again. That's C35. So now we have upper bound. So our 95% confidence interval for this population proportion is 0.37 to 0.45. This means that within the entire population of the UK, about 37% to 35% would answer yes to have you work from home question. Now, margin of error, if you want to calculate it, it would be the upper bound minus lower bound divided by 2. But there are two things I want to highlight here. First of all, you realize in Excel, if you drag this little equation, you use drag methods to create new equations into new cells. If you drag down below, it will automatically update to where you update the formula to where you have dragged. So in this case, the original formula is theta 35 minus 1.96 times h35. If you drag it down, it becomes C36. So this is the smart thing about Excel, is that when you drag down, it assumes that you want to calculate the same kind of equation but updated it on new data. That is one. If you drag it down by one row, it will update both values by row. You see, C and H hasn't been changed because you dragged one row below, but all these references has been automatically updated to one row below the original value. Okay, so in this case, because we don't have any value in H36 or C36, it gives us 0. Now this is usually very useful, and if you drag it to the side, it'll also automatically update all the data points to the side. So C, instead of C36, now it's updating to D36. Okay. You see, if you drag it to the J36, the equation becomes D36 and I36, which means that if you drag it towards the next column, it copies the function, but it also updates the data. Okay, to assuming that dragging means that you also update the data to the next, and you also want new data, right? So this is usually very helpful when your data is perfectly aligned. But it doesn't work in the case above, right? In this case, we want to use the same C35, right? And we want to use the same H35 when we drag. Okay, so you can manually enter those two, but you can also use something called absolute indexing, something that I mentioned last time. You can put a $ before each value, before the C. So now the C is becoming log. If you drag to the next, if you drag it according to the next column, the C would not be updated. It would maintain the C, because now you're using the $ before it. So you're telling it, do not update to the column. In this case, we also don't want the row to change. But if you drag it by the row, it wouldn't change anyway. So let's just keep that. And H35, we don't want it updated to I35 when we drag it over. So we put a $ before the H. And if this is the case, if we drag, copy it again, so these values become the same, indicating this during the dragging, it has not updated. Okay. Now all we have to do is change the minus sign to the plus sign to give us the new value for the upper bound. For the same reason, if we don't want, so what if we drag this particular formula? We have locked the columns indicated by letters, but not the row numbers. If we drag it down, you can see that, okay, so the column hasn't updated because it's not supposed to update it, right? But the row now has been updated to 36. Now, if we want to lock the row, we'll have to put a $ at the row as well, okay? So we put a $ here, and put a dollar sign before the 35 for both C35 and H35. Now this whole equation does not be completely locked, right? So if we drag it anywhere, it wouldn't change. Okay, so if we drag it now, you see the value being copied, but the formula is also being copied. And of course, in this case, we're dragging it. We're using the drag within the column, which means that the C and H that we locked doesn't really affect it. So if we remove the dollar sign before C and H, and we delete this one, if we drag it, copy it again, see, it doesn't change, right? Because we're dragging it across along the column. But if we use the same formula, right? So in this formula, we lock the rows, but we didn't lock the columns. So if we drag it across columns, it's not going to replicate the same value. See that? So that's because we didn't fix the column. If we drag it over, both columns is updated by +1. So now instead of C and H, it's saying D and I. That's a mistake, right? That's not what we don't want. But anyway, so this is some case called absolute versus relative indexing when you drag and copy. So basically, if you include a dollar sign before the row index, it locks the row, and if you include a dollar sign in front of the column index, which is the letter, it locks the column. Okay, does that make sense? Okay, so that's our lower and upper bound is from 0.37 to 0.45. Now again, that means that in the entire UK population, from 37% to 45% of people would answer yes to that particular question. 37.5, 47.5. You can see that's a little bit different from their estimate. So I don't know what exactly, so it means that the estimate that they have is a little bit, the method they use is a bit different from ours. It could be that they have a different estimation for the population, P, right? So instead of using the sample proportion, they use, could be 50% or something like that as the population P estimate. So the P value here, like we're using the sample P proportion, they could use something else, okay? So that's that. So that's a recap of how you construct a confidence interval for sample proportion in Excel. Okay. So in this lecture, we will spend some time with the null hypothesis significance testing paradigm. We will go to look at what exactly is p-value, what exactly is not p-value. We're going to look at the two hypotheses, the null hypothesis and the alternative hypothesis again, okay, and how they can be represented. We will look at the two concepts called type 1 and type 2 error, which should be, which I hope will be obvious during the introduction of these null hypothesis and alternative hypothesis. And also, we're going to discuss the limitations of the null hypothesis significance testing paradigm, which from now on I should just call it NHST because it's way too long of a name. And then if we have time, we will look at how do we test hypothesis about the population mean using the z-test, and how we test the hypothesis about the CC relationship using the chi-square test. So what exactly is p-value again? Again, the p-value is the likelihood to obtain the data that is equal or more extreme than what we have observed if the null hypothesis is true. So, or you can just say that the same thing, but due to random error. Remember that in the sample variation, we show that due to random sampling error, we sometimes get extreme values. And let's say sample mean, right? If we keep sampling from the same population once in a while, we get quite extreme values, extremely high or low values in terms of sample mean. And that extremity can be quantified using this probability. Okay? And here's the definition provided by the American Statistical Association. Let's look at how it differs from our definition, and so we can have a better understanding about what it is. It says is the probability under a specified statistical model that a statistical summary of the data, for example, the sample mean difference between two compared groups, would be equal or more extreme than its observed value. So here it specified a few things, right? First of all, instead of just saying null hypothesis, it is saying that under a specified statistical model. So usually in the null hypothesis testing paradigm, the null hypothesis is the default statistical model. Okay? So what they mean by a specified statistical model in the NHST paradigm is basically that's the null hypothesis. Now, instead of saying data, it specifies now that it's a statistical summary of the data, right? It previously saying that how likely it is to obtain our data. So here it's just basically saying that the data can be reduced to a statistical summary. For example, if you have two groups that you're comparing the sample means, then you can calculate a statistical summary that's called a sample mean difference. So this is more specific, a better way of saying data, because previously I was saying that how likely it is to obtain a data that's more extreme than we have observed. So in this case, it is how likely it is the statistical summary would be equal to or more extreme than its observed value. So that reduces the whole data into a statistical summary. Okay. There's some common misunderstandings about a p-value. First misunderstanding is that the p-value is the probability of the null hypothesis being true. So some people will say that because the p equals 0.05, that means the probability of the null hypothesis being true is also 5%. That is not the case. And 1 minus p is the probability of replicating an effect. Okay, that's also not the case. As I will demonstrate, as I walk you through the whole null hypothesis NHST testing paradigm, you'll see that that's not the case. The third misunderstanding is that the p-value is an indication of the strength or magnitude of an effect. This is also not the case. Okay, and it will become clear to you. I hope it will become clear to you as the whole lecture moves on. Okay, but I'm just going to show it on the screen for a little bit. Okay. A quick recap. So we already know that hypothesis testing, or NHST paradigm, utilizes two hypotheses that are statistically, that can be that are exclusive to each other, right? And they can be tested using statistical models. And the null hypothesis suggests that things haven't changed, there's no difference, there's no relationship. And HA, or alternative hypothesis, say that there is a change, there is a difference, or there's a relationship. And these can be represented with statistical models that are, but more importantly, these two represent two completely different conditions. Either one of them is true, okay? So null hypothesis can either be true or false, but it cannot be true or false at the same time. So when we talk about what statistical models is more accurate, it is very important to specify first whether the null hypothesis is true or not. Okay? Discussions under the condition that null hypothesis is true cannot be applied to the cases where the alternative hypothesis is true. Okay? So that's something to keep in mind. The null hypothesis cannot be true and false at the same time, because it's either true or not or false. So let's use an example to represent the two hypotheses in separate cases again. Okay. If you look at the SAT math score, it has a mean of 500, standard deviation of 100. Let's say that the distribution is also normal. Let's make that assumption. So if we have an associate dean in Ross College suspect that in recent years, the college is attracting students who are more qualitatively inclined, which means that their student might have a higher math scores, SAT-M scores, than the US population. Here I set a random sample of 4 students, but actually what I mean is 16. So I'm going to change that to 16. So this associate dean with a random sample of 16 students and found out that these 16 students have a SAT mean score of a math score of 550. So that's our sample mean. Okay? Now the goal is to whether we can conclude that the average SAT of all the students in this college is higher than the national average. Okay, so all the students in the college, or at least all students in the recent years, is our population that we want to generalize to. So eventually we're comparing two populations here. One is the US students who have taken the test. The other is all the students of this college in recent years. So here's a figure that represents this example, right? So the question eventually is that, is the mean SAT math score the same as national mean, or is it higher? Assuming the standard deviation is 100. Okay, our sample mean is 550. $50, 550, 20. Okay, yeah. Okay. First of all, let's represent why is the SD assumed to be 100, which is, well, it's for the sake of easy to represent or to simplify the whole problem, right? So, but SAT scores, they have I don't know, millions of people have taken this test, and they standardize the score in a way that, I think they calculate the score in a way that the standard deviation is 100. Okay? So this is assuming that the standard deviation of the population is known. Okay, so that's not null hypothesis, right? The null hypothesis basically, before we present any kind of a graph, is basically the U0 is 500. The mu is mu0, called mu0 to make it a bit easier. But we're assuming that the population mean of the college students is 500. So, but we could further turn that into a distribution of sample mean, because our sample mean is supposed to be an unbiased estimation of the population mean. Okay? So we can turn that into a hypothesis about the sample mean. And now we're saying that the mean of the sample mean should be 500. And the standard error, which is the standard deviation of the sample mean, is the standard deviation of the population divided by the square root of the sample size 16 equals 4 is 35, is 25, right? So that's our null hypothesis, right? So the null hypothesis suggests that if we randomly select a value from this distribution of sample mean, if we take a sample of 16, our sample mean is going to distribute it in this way, okay? That's our statistical model about sample mean for this null hypothesis. Okay, remember we were talking earlier about null hypothesis and statistical model, and this is the statistical model for null hypothesis. Now, we expect the sample mean to be 500, right? The mean of the sample mean is 500, but our observed sample mean, again, each value along the x-axis is now a mean of a sample of 16. So our observed sample mean is 550, okay? And that locates, and that could be due to a sampling error, right? And the probability of the observed sample being higher or equal to 550 can be determined using our knowledge about normal distribution. We know that it is the size of the area that's been cut off by the value of 550. So that is the p-value. That's it. Huh? That's the p-value. It is that. Okay? The probability of observing the sample mean of 550 in this case, given this known distribution of a sample mean. Does that make sense? That is p-value. That is p-value. So if we turn that, so this is the p-value using our sample mean, so expected sample mean. So these are still sample mean values. We can further change the sample mean to a z-score, okay? So if we use test statistics, in this case, we're using z-test. So we're now turning that into a z-score. So the original mu0 equals 500 now has been centered and scaled so that the sample mean has distribution of 0, right? Or distribution of mean 0 and standard deviation of 1, standard error of 1, okay? So now for our observed sample, we could calculate that the z-score is 2.0. It's 550 minus 500 divided by 25 is 2.0, okay? So again, using the z-score and z-table, we can calculate the p-value. And that's exactly how Fisher in 1934 defined p-value in this case. So the p-value is just the probability of observing a result at least as extreme as the test statistic. Okay, so we have converted our observed sample mean into a test statistic, which is the z-score, and then the p-value can be expressed in terms of how extreme is the test statistics when the null hypothesis is true. In this case, null hypothesis is mu0 equals 500, but in terms of z-score, that's 0, okay? Because we centered it around 0. And Fisher actually stopped there. So according to Fisher, if you know Fisher, he's the guy that proposed the NHST paradigm. But in his original definition, that's exactly how he defined p-value. It's according to null hypothesis. So any mentioning of the p-value is under the assumption that null hypothesis is true. Okay? Does that make sense? So the p-value is a concept that only applies to the condition where null hypothesis is true. Okay? That's very strict. So that's Fisher's definition about p-value. And again, Fisher only cares about H0 back in this time. Okay? Now let's represent a case where the alternative hypothesis is true. In this case, let's first talk about these individual SAT scores, not sample means, right? Let's first talk about the distributions of these individual SAT scores. So we know that the national sample, national population has an average of 500, a standard deviation of 100. And for our college, we call it UA, right? For our college sample, college population, in order to differentiate from the null hypothesis population of mu0, we call it mu A, okay? So we're saying that mu A is larger than 500. And again, for the purpose of simplicity, we are assuming that for the college population, the standard deviation is also 100, so equal to the national standard deviation, just that the mean has shifted a little bit, right? So this is the representation of two alternative hypotheses, is that the mean of these two populations actually differ from each other. But very importantly, right now, we don't know how big the difference is. Let's assume that we don't know how big the difference is, okay? But there is a difference. And we'll come to that, back to that, how big is the difference later, but we're just assuming there is a difference, okay? Now, by sampling a sample of 16 from the college, and we're also assuming, we can also say that for the national, if we sample 16 from both, okay? So the sampling distribution is going to be a little bit different from the distribution of the individual scores. The standard deviation is going to be smaller again, right? So let's see what happens for the sampling distribution, because the sampling distribution is what we are comparing, not the original distribution of the original scores. So, okay, again, this is just a representation of the blue line is the national mean. The orange dots represent the college population mean. Okay? So now you can see that these are the sample means. Now you can see that the difference of means should be the same. Okay, theoretically they should be the same, but now the standard deviation becomes smaller, right? The standard deviation of a sample mean is 25 instead of standard deviation of individual scores, which is 100. So this is the distribution of sample means. This is the population. This is the national, and this is the underneath is the our college. Okay. Again, this is completely hypothetical, what I'm presenting. Okay, so assuming that this is the case, assuming that the alternative hypothesis is true, there is a difference. Okay. And we don't know the actual location of mu A. Okay, so we know that it's larger, but we're assuming that the difference is fixed, but we don't actually know what the difference is. That's something to keep in mind. So now we are sampling from this. So now our sample, so okay, before we talk about our sample mean, we could have a critical value. So to say that if we observe something that's higher than a significant level, like if you still remember, significant level is alpha, and it is usually set at 0.05, right? So based on that probability that we set, we can find a critical value for the null hypothesis, okay? And if we extend that into the alternative hypothesis or to the population of our college population, you see that this critical value also cuts our population, the distribution of the sample mean for our college population into two sides, okay? This critical value is determined by our significance level. Now notice that the significance level is not p-value, okay? We set that 0.05, it is the threshold of p-value, but it has to be a priori determined. So we can determine the significance level is 0.05. So the area under the red line of the null hypothesis population, okay, is 0.05. That's the significance level and how it connects to the critical value. But now that critical value can also be extended further into our alternative hypothesis distribution. Okay, so now you can see that the area that it cuts to the right is much bigger than 0.05 because we know that the population, the alternative population, is to the right of the null hypothesis population, right? Okay. The critical value is alpha. Okay, so the critical value is called alpha. Again, most cases, alpha equals 0.05. It can be one-tailed or two-tailed. We can talk about that later. In the alternative hypothesis population, this cutoff area is called 1 minus beta. And to the left of the line is called beta. Again, we're talking about how a line, a value from the null hypothesis distribution cuts off the alternative hypothesis distribution. Which means if we obtain a sample from the alternative hypothesis population, if we happen to obtain a sample mean to the right hand side of this line, which is the 1 minus beta area, then we'll be able to correctly make the conclusion that there is a difference. If we happen to get a value to the left-hand side of this critical value from our college population, you can see that this value falls within to the left of the critical value, and therefore it will fail to make the right conclusion that the null hypothesis is false and the alternative hypothesis is true. Okay. So this could be further turned into if we translate that into a z-test. So this is the same idea, but now we're using a z value. Okay. So the blue curve is the distribution of z-score of a z-value that has a mean of 2. Okay. But the red curve is the z-distribution of a mean of 0. Okay. So for our case, z is 2.0, therefore above the critical z of 1.96, right? Defined by the half of alpha. Again, this is a two-tailed test, right? So instead of alpha, it is alpha divided by 2. So note that even for a z distribution with a mean of 2.0, there's a likelihood that we draw a random value from this z distribution. There will be beta likelihood that we get a value that's smaller than 1.96. That's beta. Okay? 1 minus beta means that if we draw a random value, there's 1 minus beta of likelihood that we got a random value that is higher than 1.96, even if we know that we have a z distribution around 2, mean of 2. Okay. So you can see that the beta here, which is the area to the left cut up by this critical value set by half of alpha, is determined by, first of all, where the z distribution is, which is the mean. The mean here is actually 2, not 1.96, as I pointed out earlier, how far away it is from 0, and also by alpha. Okay? If we set the alpha a little bit larger, then the beta will also be pushed back to the left. So again, this is the way to represent alternative hypothesis, assuming that the alternative hypothesis is true. Okay? So before we wrap it up, actually, let's take a break and come back in 10 minutes, and we'll continue this. Okay? Meanwhile, I'll put the attendance on the screen. Okay, let's take a break, back in 10 minutes. So I'm continuing the recording now. So that's it. And what exactly is beta? The beta indicates the probability of getting a non-significant result, even though if there's a difference. So we happen to draw a sample from sample mean to the left-hand side of this critical line, red line, right? So that's beta. And remember, we're always drawing from the population that's underneath. The population above is what we hypothesize. Okay? So 1 minus beta is statistical power. Okay? Which means that if there is a difference, if the alternative hypothesis is true, if there's an actual difference, how likely can we get a significant result? Significant indicates that we get a sample mean that's to the right of the critical value. Okay, so 1 minus beta is effect size. And in this case, because as our sample gets larger, sample size gets larger, the standard error becomes smaller, and that would also affect our 1 minus beta. So if the sample size becomes larger, let's just like do a little bit of animation, like very rough animation on this chart using the very basic, drag and stuff. So if we say that the standard error is now 10, that happens when we have 100 participants instead of 16. Okay, what happened is that this graph will become more dense, right? But the mean is still not changed, right? So standard error becomes smaller, but the mean is still the same. Now this critical value is not changed, right? So it's about here. But now the population underneath also becomes more narrow, around the same mean. Let's set it around the mean. So you can see that the beta at 1 minus beta, how does that change? Beta becomes smaller, 1 minus beta becomes larger. Okay? Because of the critical value also moves a little bit to the left, like over here. Because of the standard error, a standard deviation becomes smaller, right? So if we increase the sample size from 16 to 100, we don't know exact the value of these 1 minus beta, but we get a sense that 1 minus beta becomes larger and beta becomes smaller, which means we are achieving higher statistical power. And the way to think about statistical power is how likely, using the current research design, most importantly sample size, and many other issues like measurement, experimental material, and all that, with everything else equal, how likely it is for your effect to be replicated if there is an effect. Okay? So power only makes sense under the assumption that the null hypothesis is false and there is an effect. And p-value only makes sense under the hypothesis, under the assumption that there is no effect. Okay. So let's back to scrutinize the p-value a little bit more. So remember we at the beginning of the lecture we talk about 3 misunderstanding of p-values. But now we can know a little bit more about this. First of all, the p-value is not the probability of null hypothesis being true. Okay. This is because that we are looking at the probability of the probability of finding the findings given the null hypothesis is true is not the same as the probability of null hypothesis is true. And it is also not the same as the probability of the null hypothesis given the observation. Okay, so one is PA given B, the other is PB given A. Okay, and if you're familiar with Bayesian estimations of probability, you would know that probability of A given B equals probability of B given A times probability of A divided by probability of B. So in this case, we're interested in the probability of null hypothesis being true is PB. Okay? And in order to estimate that, we need PA as well, which we don't really know. Okay? The second is that 1 minus P is also not a probability of replicating an effect, because p-value is not informative about the effect itself. Right? So it is connected, but it does not exact the probability of that. We also know that the probability of replicating an effect, if there is an effect, is 1 minus beta, statistical power. Okay? They are connected, but 1 minus P is not exactly 1 minus beta, okay? As you have seen earlier. This largely depends on the effect size, right? So here's another way of representing a statistical power, which is 1 minus beta. But this case is a t-test. So, and the graph above indicates a one-tailed test, which all the probability of represented by alpha is congregated on one side of the distribution. So the alpha is 0.05 here, and when it's two-tailed, which means that the difference can be on each side of the null hypothesis distribution, you have to divide the alpha by 2. So now the critical t-value becomes higher because the alpha divided by 2 is more extreme than alpha itself. And also the p-value is not an indication of the strength or magnitude of an effect. In fact, any interpretation of the p-value in relation to the effect size is just wrong, since p-values are all based on the hypothesis, on the assumption that the null hypothesis is true. And remember earlier we've shown that the effect size is just basically the difference between, or in the case of difference between means, the difference between two population means. So this is the effect size, right? And again, this is under the assumption that there is a effect. And also, it is important to point out that it is extreme. Usually, we don't know the actual effect size. We can estimate effect size using the sample mean, but usually, we don't have access to the exact effect size within the population. Okay, and that is another problem. That is actually poses a problem about power analysis, because we're constantly using unreliable estimates of the population effect size. And if we don't have reliable estimates about how big the difference is, we're basically relying on sample statistics to estimate effect size, and that tend also to vary quite a lot. So this is a D is just an effect size indicating the difference between two means. There are other effect sizes indicators, such as correlation is an effect size indicator of the extent to which two quantitative variables are correlated. And R square, and there are effect size estimators. But conceptually, effect size just indicate how big is the effect in the reality. The other thing before we go to power analysis is that, as I indicated earlier, if the sample size gets bigger, then it's more likely to find a significant result, because the standard error of the sample mean will also become sample mean distribution will become smaller and smaller. And if you think about it, it's not hard to come up with the conclusion that even the effect size is very small, it can be significant at some point if you have a sufficient large sample size. So this poses another problem about the p-value, is that it will be significant once you have reached a certain number of sample size. Now then the problem becomes, even though if it's a significant result, you have to think about whether the difference is meaningful in real life, right? If it's a very small, tiny difference, although it's significant, sometimes it's not important. But sometimes insignificant results even with a small effect size can be very interesting. For example, if you talk about the death rate, right? A death rate of a difference of 0.01% of death rate when it's multiplied by a large population can mean a large number of deaths. So there are cases where, so you have to think about p-value, but significance is not everything, right? So as a result, effect size, that's my cat meowing. As a result, the American Statistical Association actually encourages using alternative methods and not relying solely on significance testing. Yeah, he's begging for food, and that's what he does. And that, if you hear that, that's his scratching post, like the sound like scratching. Let me just grab it. Yes. And yeah, I think we all needed a little bit of that. So what the American Statistical Association is saying is that we should not just rely on testing, we should also use method that emphasizes estimation, like confidence intervals, credibility, prediction intervals, or Bayesian methods, or Bayesian factors, Bayes factors. And if you're interested, you can look into Bayes factors, because Bayes factors can actually tell you how likely or how unlikely is the null hypothesis being true of given the evidence at hand, right? Remember earlier, the p-value cannot tell you that, but Bayes factors can actually tell you using a value to indicate how strong is your evidence favoring null hypothesis or the alternative hypothesis. And I'll let it go. All right. So let's do a quick exercise on G power, looking at how statistical power, again, statistical power is just how likely your results will replicate, how likely your effect will replicate in the long run if you fix the sample size and you fix the effect size, right? So let's go to G power and take a look at how G power can help us to do that. Okay, so now I have G power on the screen. You can see, as again, it's a very dense, very technical program, but it is quite cool. So let's look at select. You can, first thing you should do is to select test family. Okay, so you can have exact F test, T test, chi-square test, Z test. So let's say we want to do a Z test, right? Because that's the simplest. And there's so many different Z tests you can see. And the difference between two correlation coefficients can be submitted to a z-test. Many things can be submitted to a z-test, but let's say that just to make it simple, we just do a generic z-test, which basically give you a z value and give you. And then type of power analysis, you can also see there are different types. The first is called compromise, compute alpha and beta, given beta and alpha ratio. Non-centrality parameter, which is basically the mean of the z value. Okay? We can also compute alpha, we can also compute power, or compute how much of a z-score you need. That would be sensitivity. So let's select postdoc compute power. Okay. Now you can see that there are input parameters. There are 4 input parameters to work with. The first is called tails. You can do a 1-tail test or you can do a 2-tail test. Non-centrality parameter mu is basically the how do I say the mean of the z distribution that you want to test against the 0. So this is, consider this as the z-score that z-score that actually exists, that depicts the difference between the two population means. Okay, let's say if the two, I'm gonna let my cat out first because he wants to go out. Okay. Does your cat also like meow like that? All cats sound the same? I don't know. Okay, so let's say the mu, started with mu of 1, right? Which indicates that in terms of, just think of it this way, in terms of z value, our population, the population that we're testing, the average is 1 z-score away from 0, right? And if we set the standard deviation at 1 and alpha value at 0.05, again, this is not a p-value, this is the alpha value, because this suggests that we are a priori define an alpha value, okay? Now, if we select all these and calculate, and then the distribution of what we're testing is depicted in this graph, and it also has some numbers popping out at output parameters. So we see that the beta error probability is 0.082, which means that if we're testing a z distribution that has a mean of 1 against a z distribution that has a mean of 0, okay? And again, we know there's a difference, right? In this case, the alternative hypothesis is true. We know there's a difference in terms of these two distributions, and that difference is 1 z-score. Now, if we randomly sample from a z distribution that has a mean of 1, then the beta suggests that 83% of the time, we will get a value that is lower than the critical value defined by half of alpha, which means that 83% of the time, we come to the conclusion that there is no difference, okay? So only 17% of the time can we get a significantly different, can we get a significant results in that we get a z-score that's higher than the critical z-score defined by alpha divided by 2. So you can see that in this case, the statistical power is not very high, right? Now to increase that value, right? Imagine that what z value is determined by the difference of mean divided by standard error. So if divided by standard deviation or standard error. If we make the standard deviation smaller, then the z value will actually increase. Okay, so now if we say that the Z value has increased to 2, right? So if we change non-centrality parameter mu, we set it at 2. If we calculate again, we notice that, first of all, the Z distribution, the one that we're testing against, 0 has moved to the right. Now, this cutting point, the critical Z, is not changed at 1.96, right? But now, since we have moved the Z distribution to the right, the beta has become smaller. So it's less likely we draw from the population of Z with a mean of 2 that a non-significant result. Actually, it's only 48% will get a we're wrongly saying that there is no difference. So 52% of the time we will correctly infer that there is a difference between these two distributions. Okay, so that's Z-test, right? So to keep it simple, we just keep it to the difference between two means, because that's somewhat the most straightforward way of showing that how beta and alpha works. If we change the tails to one tail, then you can see on the screen that on each side of the null hypothesis distribution, there is a cutoff point, right? And each side shares the proportion of the probability of alpha divided by 2. Now, because this is symmetrical, it adds up to alpha. If we have one tail test, if you click on one tail and keep everything else the same and calculate it, and then we notice that this critical Z value has been moved to the left. Now it's 1.64 instead of 1.96, because we now have the entire alpha of 5% to the right-hand side of the null hypothesis distribution. Okay, now you can see that by changing this, effectively changing the alpha that we are testing, we also decreases our beta to 0.36 and increase our power to 0.64. So now there's a 64% of likelihood if we randomly draw a Z value from a Z distribution with a mean of 2, that the Z score will actually higher than 1.65, okay, which is different from 0. Now let's move on to a different test family. We call it, let's say, t-tests. Okay? If we select t-tests, and then there are different options, we have different statistical tests, right? You can see that all these are done with t-test. If we select the means difference between the two independent means, so we are comparing the means of two groups, so the means from two populations. We select this, right? And we can also choose the type of power analysis. Now, you can see that, let's play with the first option called a priori, computing required sample size given alpha, power, and effect size. So this gives us basically this power analysis will tell us how big of a sample size do we need within each group given the effect size. Do we need to achieve certain degree of power, right? Again, power can be think of as how likely is our results going to replicate if there is an effect. How likely is it we are going to replicate the effect in another study using the same setting, right? So running the study over and over again, how likely this effect actually appears. Effect size D, smaller is smaller and larger is larger, and 0.5 is quite a large effect size, right? Alpha, we set it at 0.05. Tails, we set at 2 tails. Now, statistical power. We start with 0.06. Let's say we want 60% of the time we can replicate the findings. So let's say we want our statistical power to be 60%. And this allocation ratio just means the ratio of sample size of group 1 versus group 2. If we set it at 1, we're saying we want equal sample size in the two groups. If we calculate that, we can see that to achieve a power of 0.6, if the effect size is 0.5, then we need 41 participants per sample, per group. You can say the sample size group 1 and sample size group 2 are both 41. So the actual power will be 61%. And it doesn't really say here, but yeah, okay, power is 1 minus beta, which means 40% of time, if we use this particular sample size, 41 per group, if the effect size is 0.5, then about 40% of time, we won't be able to find a critical value above the critical T. Okay, so 40% of time we won't be able to detect the difference. Now let's see, what if we change the effect size to 0.25? If we change the effect size, we're basically saying that the difference, there is a difference, but the difference is quite small, okay? And a smaller difference, given the same amount of power, do we need a larger effect size? Do we need a larger sample size or a smaller sample size in order to reach the same level of significance? If we run that, you can see that now if the effect size is only 0.25, then we would require 160 participants per group to achieve the same statistical power, right? So when the difference is smaller, we will need a larger sample size to achieve the same statistical power. Okay? Now let's keep the effect size as 0.05. Let's say that we want a higher statistical power. Let's say that like 60% is just not good enough. We want to make sure that the effect can be replicated, the results can be replicated. We will be able to detect a small difference more often, right? So let's say 80%. So 0.80, we change the power to 0.80. And again, with a very small effect size. Actually, 0.05 is not even a small effect size. We'll see that now we need 253 participants per group in order to achieve a higher power. Okay. Okay. So and you also so this just illustrates how sample size, effect size, and power are interconnected, right? We can also post hoc analysis, right? There's a post hoc option saying computing achieved power. Now, sometimes we read a study that reported a certain sample size and the effect size. And we want to know that how likely is that study going to replicate if we are going to do the study. You know, like before, it's usually recommended that if you want to pursue someone else's line of research, you should want to see that how likely is their results going to replicate, right? And this could be done in what we call the post hoc power analysis. Is, if you read it, is a compute achieved power given alpha, sample size, and effect size. And if we say that it has a small effect size of 0.05, alpha of 0.05, which is most researchers will use that, two-tailed, most researchers will use two-tailed. Even if their hypothesis is a one-tailed hypothesis, most people will still do a two-tailed test. Now, let's say that this study has a small sample of, I've seen like studies with 20 participants per group. Let's say it has a 40 participant per group. That's what they reported. We want to see how likely are we going to replicate this finding if the effect size estimator is somewhat accurate. So we put if sample size per group at 40, 40. If we calculate, we see that their power is only 20%, less than 20%. So which means that if this effect size is really that small, and if the sample size is that small, then if we run the same study with the same sample size, there's only 20% of likelihood this study the effect gets replicated. The significant effect gets replicated. And this is what we usually call, we usually say when a study is underpowered, right? Small effect size, small sample size. Yes, they have reported a significant result in terms of p is smaller than 0.05. But if we run the power analysis, we'll see that this effect is unlikely to replicate. Okay? In fact, a lot of studies are severely underpowered due to the difficulty of finding the sample size, finding an adequate sample. For example, a lot of the baby studies, you just cannot have 100 babies to run in a study. So for those studies, like this cannot be solved in the power analysis. So a lot of the researchers who study a baby, they have to rely on combining a lot of studies and to run what we call a meta-analysis in order to understand certain effects better. So of course, if an effect size can be bigger, I think if it's at 0.45, if we keep it at 40, keep 40, but the effect size is now a little bit larger. And then you will have a slightly higher power. So in this case, you have a 50% of 51, a power of 0.51, which means if the effect size is bigger, with the same sample size, it is more likely to get replicated compared to a smaller effect size. Okay, so that's that. That's how to use G-power. Again, you can see that there are so many different options, which means that this is a very powerful tool to do power analysis. And there are F-tests, there are chi-square tests, goodness of fit test, that kind of thing. So it's a very powerful and useful statistical tool to run power analysis. What power would you aim to get for a study? Lisa has asked. Okay. It is only until recently that people started to care about power analysis, because people started to find out that a lot of studies are just not replicable, including classical findings in social psychology, especially. So, and you will see that in a lot of the older publications, they don't report power. They don't report statistical power because they are severely underpowered. Okay, so but nowadays people will suggest 80% as something that you should aim for. Like power, you should aim for a power of 0.80, and also if you don't have a good estimation about effect size, like for example, if you don't have like 20 studies that already been done on the same topic that give you a more accurate estimation of effect size, it is recommended to use some kind of a moderate effect size defined by Cohen, I think. I think it's around 0.4 or 0.45 will be considered as a moderate effect size. I'll put that effect size on next lecture, but I forgot like the exact cutoff. But for certain effect size indicator like Cohen's D, which is the difference between two means, I think 0.45, two means divided by the standard deviation. 0.45 is a large, it's a medium effect size. So a lot of people use that to determine the sample size. So nowadays, publications, journals are requiring you to report how you determine sample size, right? So one way is to use a power analysis. Okay? So that's the current best practice. So if we use, for example, t-test, if you look at the g-power, you could have an a priori compute required sample size. So if you have a 0.45, power of 0.8 will require 80 participants per group. Okay? And that's way higher than the recommended minimum of 40. Like I think some earlier researchers have a recommendation that you need at least 40 observations per group if you use a between subject design. That is, if you randomly assign participants into different groups. Okay? But now what we are showing here, if you want to achieve 80% power with an effect size of 0.45, which I believe is medium effect size, you would need 80 participants per group. If you want to play more with it, you can look at the difference between two dependent means, right, which is matched pairs, which means that you have a within subject design that instead of randomly assign participants into two different experimental groups, you have participants going through both experimental conditions. Imagine if you want to do a study where the noise level affects, I don't know, affects fatigue, then you can have participants going through both high noise level and then later to a lower noise level and measure the fatigue in both conditions. Then you would have a within subject design. So in that case, if for within subject design, as I'm putting it on the screen right now, so which means that you have a t-test, but it's now matched pair t-test. If you want the same kind of effect size of 0.45, oh, by the way, you can determine, you can click on determine, you will pop up a different value, a different little paradigm window. But you can just run the calculation here. You can see that for between subject design, for within subject design, you will actually need smaller sample to achieve the same power. So you only 41 n equals 41. You only need 41 participants in the group. There's no group like that. You only need 41 participants instead of the 160 to achieve the same power. Okay? So this just shows you that within subject design, experimental design, which we haven't come to that yet, but I hope what I said was intuitive enough. So if you have the same participants going over the two experimental conditions, you will actually require much smaller sample size compared to when you have randomly assigned participants into different conditions. Okay? Okay, going back to our PowerPoint slides. Okay, so we're gonna. So we never really talk about these two types of errors, but now after we have learned alpha and beta, we know that it's not too difficult to understand the two types of errors. So if the probability is less than alpha and we choose to reject the null hypothesis and accept alternative hypothesis, then there is a probability that our results is due to actually by chance. This is called type 1 error, which is false positive. And this is completely determined by a priori by our significance level alpha. So we can set a level of type 1 error. We set the level of type 1 error when we determine alpha. And type 2 error is so again, a little bit more about type 1 error. So if the significance level is 1% instead of 5%, right, then we will have a tighter significance level. And the probability of type 1 error is 1% in this case. Okay? The type 2 error happens is also called false negative, which means that there is a difference, but our results have failed to correctly detect the difference by having the p is larger than alpha. Okay, so false negative is called type 2 error, and the type 2 error rate is beta, and beta we have already seen that in the previous slides. And we've also known that the determinants of beta is determined by alpha level, effect size, and the sample size. Right? And again, statistical power is 1 minus beta. Okay? Again, statistical power is when the alternative hypothesis is true, how likely our procedure can correctly reject the null hypothesis and accept the alternative hypothesis. That's statistical power. And that translates into how likely our study can be replicated under the exact testing conditions. Okay? So that's the two types of errors summarized. There are different ways of calling these two types of errors. Some just call type 1 error alpha error, or type 2 error beta. Some call type 1 error the false positive, type 2 error false negative. And we can also see that when we make a correct decision, that means that there is no difference, and we say that we accept, we did not reject null hypothesis, or there is a difference and we correctly rejected the null hypothesis based on p-value. Okay. So this we already mentioned earlier, the larger the effect size, the smaller the p-value, and the larger statistical power. So eventually a very, very small and trivial difference can become statistically significant if you have large enough sample size, but then it becomes a matter of determining whether that difference is realistically meaningful. There's one-sided versus two-sided test, which I have presented to you earlier. For two-sided, which means that the alternative hypothesis is non-directional. The same, for example, if you say the null hypothesis have a probability of 50%, then if it's a two-tailed test, it is basically saying that it will be different from 50% without specifying the direction. Okay? And again, in most of the cases, even if people have one-sided hypothesis, they still run two-sided tests. It becomes some kind of agreed norm to do in the quantitative research. First of all, finally, you might have already sensed that there's a strong link between the hypothesis testing and the confidence intervals. For example, to perform a test on mu on the population mean is just to find a confidence interval of means and check if the mu actually falls inside a confidence interval estimated from the sample mean or not, right? So if you follow the test with a 95% confidence interval, will give us more insight into the actual value of the mu, right? Okay, so let's take a break and come back in 10 after 3, and then we will have, we'll go to some actual hypothesis testing statistic using a chi-square and using z value to test some hypothesis. Okay, back in 10 minutes. So this is the data that was from the survey, and they only gave us observed percentages. So this has been already been turned into a I believe conditional percentage table. Remember, so like each for each cell for each category they add up 100%. In this case, 99.9 because they have to do some roundup, which is causing some problems later. you'll see. So, but they did tell us the n, right? So we can, based on the n, which number of female and male in this survey. So female has 320, male 340. We can reproduce to our best estimate the counts, the frequencies. So these are, you can see from the equation. Again, if you double click on the cell, you will see the equations, right? So this is H43 times H41 divided by 11. Divided by 100. So that gives us the n times 30.6% and round it up to 104. So this gives us the best estimate of the frequencies. Now the tricky bit is this: these frequencies, if you look carefully, they're not rounded up, right? So I have rounded up. I have already rounded up because I formatted them to display 0 places. If you have 1 decimal places, you'll see that like some of them have 92.5. I don't know like what exactly frequency is, right? Because you cannot have half count. So so that creates a little bit problem that you will see. That problem was avoided by moving these values, rounded up values of these frequencies into the table to the left. So here you can see the equation inside is called round J40 by 0. Okay, so now I wanted to round it up. This is a round function. It takes the number, a number of digits, so it now becomes rounded. So now you have all rounded data. By the way, the convenience bit again is that if you have, if you just drag it, now that's again a great thing about Excel. If you drag it across the cell, across the rows, it kind of automatically updates to the same kind of correspondent cells. So 143, if you drag it here, it automatically updates according to 127 to the right. So okay, those are checked up. Now you can see that the total number of participants are different from what they actually told us. We have 339 and 319. Who knows? Like some round up. But to make sure that we don't use these 340 and 320, we use our estimates, right? Now this is the observed frequency per cell. So this is the observed frequency table. We can get to a, if we sum up on the row, we get row, total people who responded yes, not able to, or no. Okay, so it seems like it could be the case that the women are more likely to say, there are more women saying that they are not able to work from home than male, right? So that's a guess. By the look of the data, it seems like it's going towards that direction. So, but what we are really interested in, again, is whether this is beyond random, right? This is beyond, if this is extreme enough to say that there is actually a relationship between gender and working from home, responses to working from home question, or not. So in order to do that, we need what we call expected frequencies. So expected frequencies, okay? So this is, so the second step is to acquire, to acquire the chi-square. So let me explain to you what exactly the chi-square is calculated before we go back to the data again. So the second step is to produce the test statistics. We have the frequency table, but we want to turn that into a single test statistics that we can then determine the probability of obtaining that statistics or more extreme than that, right? So the chi-square test basically says us whether we tested whether the two categorical variables are independent or related. So this is a form of a non-parametric test. Therefore, it actually makes sense to put it before all the t-test and z-test, which are parametric tests. So which means that it doesn't really, the data do not need to meet the so-called parametric assumptions that are usually involves independent samples, normally distributed data, equal variance across groups. So these non-parametric tests do not need to require to meet these assumptions. Okay, if you hear that a test is parametric, that means that these assumptions needs to be met. Instead, it has its own assumptions. So, such as, for example, you need to have independent observations. So the male and females are independently observed. If it's a 2x2 table, all expected frequency should be larger than 5. For a larger table, you need to have certain, so you need to meet certain criteria that there has to be a certain amount of expected frequencies in each cell. So if these assumptions hold, then the chi-square test follows a chi-square distribution. Okay? And I think in our case, the independent observations are not exactly met because the responses to questions are not exactly independent of each other, right? If you selected yes, you could not select no. Okay? So that to keep in mind. So this is how the test statistics are calculated. You have observed frequency, and you also need the expected frequency. And expected frequency is calculated through this formula. I have a total column times row total divided by table total. Okay. So basically, the chi-square will add up all. It's a sum of all the observed counts minus expected count squared divided by expected count. But basically, it just says that how much do the observed values differ from the expected values. So in order to do that, we go back to this table, right? So now these are the expected observed frequencies. In order to calculate the expected frequencies, we just have to, for each cell, if you double click, you can see that it has an equation. So again, this really shows how the colors works to make sure that the equations are correct. So this is basically the column n, which is the blue, times the red, which is the row n, divided by the total sum, right? And you can notice that I'm putting dollar signs where I don't want that if I as absolute indexing. So the E50 is always fixed when I drag to reproduce to recreate. If I want to use the drag function, if I use the drag to reproduce the function, I want certain things to be unchanged. So this total n is unchanged, and the row 50 is also unchanged. So this one only updates according to the row. So this formula will update to the row because the 47 is not fixed. Okay. So for the column one, I left the column free, and for the row one, for the row n, I left the row free. So when I just simply drag to reproduce to replicate, and it would automatically apply the same equation to the next row, okay? And this automatically apply the same equation to this row. But the column is not changed, and the total is not changed. So the same equation here, and now I'm applying to the column n and row n divided by the total. Okay? So again, if I just drag this formula, the same cells to automatically produce the formula, it gives me the right updates. Okay? This wouldn't happen if you put a dollar sign or if you remove the dollar sign before these equations, within those equations. Okay? So that's the second step. So these are the expected frequencies. The third step is to produce what we call residuals, which is observed minus expected frequency. Okay, so for this one is C40 minus C47. If we zoom out a little bit, we can see that that's the difference between 143 and 139. And again, if you have one formula here, and if you don't put any dollar sign, and just drag it across the whole field, it automatically updates to the correct differences. Okay? Okay, so that's residuals. It's observed minus expected. You can see that all the residuals adds up on the row adds up to 0, and on the column also adds up to 0. Okay, again, we are not really meeting the independence, the assumption of independence here, because the response to no is not independent from the response to yes or not able to. Instead, they're actually determined by that, right? So I'll keep that in mind and see how that affects our results, test results, in the next lecture. But here we just move ahead, assuming that they're actually independent. So now we create chi-square points for each of the cells, which is basically observed minus expected time, what did I say? The power to the 2 divided by the expected. Do I need to add them together? Let me see. Yes. So okay. So those are the chi-square points. So basically, these values power to the 2 and divided by the expected. We got chi-square points, and then if we add up all the points, we get. So you can see this is a sum of all these values. We have the chi-square. In this case, chi-square equals 1.7. So that's our chi-square statistics that we obtained. Okay. So the third step is to find the p-value. So remember that I mentioned earlier that the chi-square distribution depends on the degree of freedom. So different chi-square with different degrees of freedom has distribution of different shapes. So how do we find degree of freedom? We basically use row minus 1 times column minus 1. So the number of rows is 2, number of columns is 3 here. So we have degree of freedom of 2 minus 1 times 3 minus 1 equals 2. So that will be our degree of freedom. Okay? So we have degree of freedom equals 2. Now the p-value is determined by looking at the critical, well, we can do two things here. We can compare the chi-square we got with the critical value that we know at the chi-square degrees of, with degrees of freedom of 2 at 0.05. So by doing that, we can just look at this, this little table that I presented on the screen. So you can see that in order to reach for degrees of freedom of 2, if you want to exceed the critical value, you need a chi-square of 5.99 in order to reach the critical value that's at alpha level of 0.05. So that's the critical value. So 1.7 is actually it's not larger than this critical value. Therefore, the probability is less, p is less than, is larger than 0.05, and therefore it's not significant. Okay. What we could also do is we can use a function in Excel in order to get the p-value. So this function is called chi-squared.test. Chi-squared.test. And again, if you drag over, if you hover your mouse over this function, it shows you the arguments it's going to take. So the first argument is called actual range. The second argument is called expected range. So basically, it takes two values, two arguments. The first argument is the actual observed frequency. The second argument is the expected frequency. So in this case, you only have to, when you use this function, you only have to select the expected, the observed frequency as the first argument. Let me just delete both of you to see how both of the two arguments and see how you can actually select. You can just select row up and just select these as the first arguments, right? So you can still see the function in the function window, and then you can click on this after the column, after the comma, and it will ask you to select the second argument, which is this expected range. And now you have both. If you select enter, it gives you the p-value. So the p-value in this case is 0.43. Again, we already know it's going to be larger than 0.05, and therefore we conclude that we could not reject our null hypothesis that there's no relationship between gender and the way they respond to this question. So there's no difference between not able to work from home between male and female. We can have another function, a different function is called chi-squared dist.rt. You can see that this is another function that also gives you the p-value, but with a specific chi-square. Okay, so in this case we have chi-square of 1.7. So you see, like, it takes the argument of 1.7. The second argument is the degree of freedom is 2. So our p-value is, you can see we have the same p-value of 0.423, which rounds up to 0.43. So two different functions, we got the same p-value, which means that this chi-square was correct, that we calculated. Another function here is called chi-square.inf.rt. Takes two arguments. That the first one is the alpha, is the significance level. The second is degree of freedom, and this gives you the critical value that's required to make for a significant result chi-square value. Again, we already know that it's 5.99, which we learned from the previous, from this table. You can see that with degree of freedom is 2, alpha level is 0.05, the critical value is 5.99. Okay, just using different methods to obtain the results, the same results. So now that we have already got a p-value, and it's not larger than, it's larger than 0.05, we can conclude that the data is not strong enough to reject the null hypothesis, so that therefore we cannot reject the null hypothesis. Okay. So that's a full cycle of how you use these 4 steps to conduct a chi-square test. I've also showed you how exactly these chi-square statistics was obtained. The next exercise, now let's do an exercise to test whether there's gender differences that in terms of among those who said that they're working, what exactly are they actually, is that gender differences in that, right? So we have, these are the 4 options, right? Work from home, didn't travel to work, didn't work from home and travel to work, both work from home and travel to work, didn't work from home and didn't travel to work. Okay. So here are the distribution of the probability. And if we look at the results, it seems that male is seems to be relatively more likely than female to say that they didn't work from home and travel to work. So more male seems to travel to work than females, and the other way around for female, right? So female tend to work from home more and male tend to travel to work more during this pandemic. There are also some differences on how they reported both have worked from home and travel to work. And both didn't work from home and didn't travel to work. So these two options, the gender difference on these 2 options are a little more confusing, right? Because if a male has reported that they have gone to work, then the female means that the female in the household also went to work as well. So I don't know what these differences on these these 2 options mean. But anyway, so I'm going to pause the recording now as we work across this problem, and